memory fp, fp plus 28. This is like one instruction. One instruction will tell you this.
Okay.
This is like
so how does this relate to the fact that the memory you say is read-only?
Because, for instance, if you want to compute the difference of two things, I don't know if you want to compute x minus y and store the result, what you will say is that you will have one dedicated cell that will store the result, and you will transform the difference into an addition, and then this will become one instruction that will assert that this cell corresponds to the differences of these two cells.
Okay.
But once in the memory is represented as a big vector, and once you write something inside the cell of this vector, this is forbidden to rewrite something again on this same cell.
So it's like write once and not read only.
Right.
Yeah.
Another way of saying that's immutable.
Okay.
But you can still use that cell for assets.
Yeah. You can see it as write once, or you can see that it's because from the point of view of the verifier, there is one memory which has been previously filled by the prover, and you simply assert that some relations between the cells are valid. But you can see it as write once, and if you rewrite, you must get the same value. It's equivalent.
But I mean, if one then does, like an assertion by saying add of element plus 0 equals to something, to something that was written to that memory location before, then that wouldn't be valid, no? Because the add instruction would still technically write to the 0.
I think is the add instruction just. I think we just have an execution trace, and we're just checking constraints against the constraint.
Yes, we're on the verifier side. So
Yeah.
verifier
Oh, I think we should think about all this memory is like an execution trace that's being committed to.
Okay, so we are already there. We're not talking about execution. Okay.
Yeah, sorry, I think I was getting confused about this one.
So is it clear those add and multiplicate relations between memories? Okay. And as I repeat myself, but it's relative to FP. So you cannot do memory index 3. Not possible. It's always relative to FP. Okay. So there's two first opcodes. Third opcode, dereference. Dereference opcode basically lets you do this. Memory index. Memory FP. I will take a constant like 7. And it could also be a constant like 500. So it lets you access memory, but instead of indexing relative to FP plus constant, it's indexed with a cell in memory. So it's like dereferencing a pointer. And this is useful because previously we were able to manipulate memory only relative, like inside our current frame in memory. The discussion in this frame is abstract, but when you want to program using this ISI, you need to have to conceptually think in terms of a stack or frame of memory. And using this instruction, you can write somewhere else which is not in your frame of memory. And for instance, how will we implement function calls? Because you can see that each function has its dedicated frame. And if you want to jump on another function, you will need to allocate another frame. So for instance, this is the memory. This is like the current value of FP, and this is your current frame. And you want to call a function with some arguments. And so what you will do is that you will allocate some chunk of memory, you must know in advance at compile time that this function will consume 20 feed elements. You must know the memory footprint of each function. And the idea is that you will be able to, so this is the memory, but there is also the bytecode. This is the bytecode, and let's say currently we are here and your function is here, so we'll have to jump into the bytecode to the location of your function, but at the same time you want to jump in memory so that you want, because if I take some advance, there will be a jump. This is the last opcode. There will be a jump opcode that enables you to modify the program counter to go at the location of your function in the bytecode, but at the same time you want to modify your frame pointer because you want to access fresh memory. And so the key idea is that in K-row, for those who are familiar with K-row, you have one register, the allocation pointer, that points in memory to the last used, like in memory, the allocation pointer points to the part of memory which is still free to use. But here we don't have the allocation pointer. So the idea is that when you want to jump to a function, you will receive as hint the pointer to a new location, to a new frame. And for instance, if this is 20, you will receive as a hint this value, which points to a new frame that the prover has allocated to execute this new function. And the key idea is that because it's read-only, from the point of view of the verifier, you don't care where this new chunk of memory will be allocated. The prover could allocate it here or here, here, you don't care. Because from the point of view of the verifier, everything that will happen then will be the same because the relations between the cells will be the same, and you do not risk, important, to overwrite previously written chunks of memory because it's read-only. And so that's why you can give the prover the liberty to allocate this chunk wherever he wants. And so when you want to call a function, the prover will allocate a new chunk and will store the location of this new chunk in the current frame. And then there will be an instruction to jump to the bytecode of your new function and to update FP with this new value. Yeah. And okay.
One question: why cannot like the hint be malicious? Like I say, yeah, I'm going to the right function, sure, and then you move it to another place.
Because actually you can, if you put 201, it would still work because all the computations that you will do, it's read-only, so you will assert the same things between the cells, and when you will come back, because actually you will store the arguments and the results that you call your function. Like if you want to call your functions with an argument, like your function f has, let's say, 2 arguments, you will store the argument at the beginning of this frame using the dereference instruction. Because using the dereference instruction, you can, before jumping, you are still in this frame, you can access the value here using this dereference instruction. So before you jump, you store the arguments you want to call your function with. You jump, you do a bunch of computations, and also before you jump, you also need to store the current frame pointer, and the current will also store the current program pointer. Because after you jump, you execute your function, in the end, what will happen is that your function will jump back here and here.
So Emil, so jump is used for calling a function, returning from a function,
Yes.
as well as local flow control within a function.
Correct.
Okay.
Correct.
I guess I'm a little unclear on what the spec for jump is. Like, what are its operands?
Do you have your computer?
Yeah.
It's. I think if I can take a look.
And okay, so jump is a conditional jump.
It doesn't. Oh shit.
Is your keyboard dead?
It's not my laptop, but it doesn't work quite well. Okay.
Would you like to use mine?
No, I will use mine.
Oh, I see. That's the university's laptop. Tragedy of the commons.
You're familiar with Cairo, right?
Yeah, kind of.
Why didn't Cairo do this? Why do they have the extra register?
The other one,
Yeah, they have
The
like
AP?
Yeah.
I think it was like a kind of whole thing because in the new one they don't have.
In the new one, they don't have it.
Yeah, I think
Okay.
they have replaced it.
Because Cairo M doesn't have it. either.
Yeah.
But the new one from Starkware it also doesn't have it.
I think the new one from Starkware
Oh.
is the Cairo M.
Oh, I thought Cairo M was from Kakarot.
Yeah, but when we asked to Maya, she told us that they are kind of collaborating.
Oh, really? Okay.
Sounds like a case of convergent evolution.
Right.
Nice.
Can everyone see the screen clearly?
Excuse me, but does every frame always have a program counter and frame pointer cell in it?
Sorry?
Does every frame have a cell for a program counter and a cell for a frame pointer?
Basically, every frame has FP?
FP and PC?
Yes. Because this is like about two register values that at any moment you have one FP and one PC. Okay, so if someone has a better computer than mine, I don't know why it crashed. Okay, it restarts.
What's the Wi-Fi, by the way?
Guess Wi-Fi.
I don't have an HDMI port. They keep stealing our ports.
I mean, I still do, but on my laptop, it's a pain in the ass to get anything working. Like, I have to activate my NVIDIA GPU that's in there, in the BIOS, because otherwise, you know, like, internally, it's routed so that the HDMI port cannot be used if it's disabled, and then only the HDMI port works, and the display port also has never works, and
If someone has a
That sounds
laptop,
like
just
software.
yeah.
Or you know?
At least, I suppose on Windows, it's my.
I've traveled for work in the last couple of years, and I discovered both my laptops would no longer move. So I was like, okay, let me fix this, open it up, look at the battery, can I find a replacement for this battery? No. So I had to get a laptop.
Oh. So that's why it runs Windows, huh?
Planned obsolescence, intentional non-repairability.
Mm-hmm.
Okay.
There you go. I don't know what you're gonna find on here.
Okay. Okay. Perfect. So the question was the details of the jump instruction. Perfect. Okay. And as you said, it's a when you want to call your function, before you jump, you write at the beginning the frame pointer, the current frame pointer. And so then you can jump, and in the end, after your execution, you can jump back using the same instruction, but in this case, the value, the updated value of FP will correspond to the previous value of FP because you have stored it here.
Yeah, I'm trying to sleep.
Okay, and as you said also, we can use this jump for control flow, so if else, in which case you will not update the frame pointer. You will simply jump into different locations of your bytecode, but you will stay in memory in the same frame. But typically in your bytecode you could have some kind of this is the start of your function. You execute some instruction, and then you have an if-else in your bytecode. And how will this be implemented? Using two blocks of bytecode, and you have a conditional jump that will either go here or go here. And in the end, both blocks will jump in an unconditional way to a common continuation of the bytecode.
So if you do a function call, you need a return address to go back, right?
Yes. Yeah.
So because we don't have a return or a stack to put the address in,
Yeah.
the compiler needs to pre-compile the return address itself.
No. There are two things. When you return, you need to know the PC you want to return to and the FP you want to return to. And both values will be stored in memory at the beginning, like if
Of the frame.
yeah. This is so you were here, you want to jump here. Before you jump, you store here frame pointer, and here program pointer, and here first argument, second argument, result.
Okay, so it's passed as input to the function.
Exactly. Exactly.
But so the program counter and frame pointer, like as a register, essentially they are really stored, like the current values are actually operating on, they are stored independently outside of memory.
Exactly. There are two values independent of memory, FP and PC, and this is like really independent of memory, the current PC and the current FP. And here, what you store is that at the beginning you store your current FP and PC, then you jump, and when you jump, these values correspond to your previous PC and your previous FP. Mm-hmm. That will be useful to come back to your previous context.
And so it's a stack, but with only 2 slots.
Yes.
And so when you jump back, do you then increment the program counter relative to the value that you had stored, so that you actually jump to the instruction after?
Correct. Okay. Correct. Actually, when you store the PC, what you do is that you don't store the current PC, you store current PC plus 1. Yes, correct. And with these 4 opcodes, null, add, deref, and jump, you can do, so you can call functions, return from functions, if, else. What you cannot really do is loops, because in Kero, you could, for loops, and I'm not a Kero expert, but I guess it's done like that. You could have your loop to stay in your frame. Yeah, you could. I think I'm not sure, but I guess that in Kero, when you have a loop, you could keep the same value of FP, and just at each iteration of your loop, you consume more memory. And because you keep the AP register, you can know. You keep track of how much the memory has expanded. But in this context, there is no AP, so we must know at compile time the exact size of the exact footprint of each function. And so you cannot have a loop of unknown number of iterations in your frame, because each iteration would consume some more memory, so you would run out of memory inside your frame. So what you do is that you use a compiler to transform loops into recursive function. And it's doable. Like, for instance, if you have a loop that, for instance, a Fibonacci, you can implement it using the loop, but you can also implement it using recursive run. And it's possible to tell a compiler to convert all the loops into recursive function. And using recursive function, when you have a new iteration of a loop, it will allocate new memory. There is some overhead, because it will have to store the PC, the FP, jump, do the computation, jump back. So there is some overhead, but the benefit is that you don't have to store, you can remove the AP register at the cost of having to store some values in the beginning of each new frame. Yeah.
But if you transform loop into what's called compiler technology, continuation passing style, okay, you actually don't need to return back. You can use tail call optimization, so you just continue and you never jump back. So you can actually not store those frame pointer and instruction pointer.
I think I see what you mean. And this is, I think this is
this is called TCO, technical optimization, and well, it's unfortunate, but the technique is called continuation passing style, but it's not continuation in the KVM.
Okay.
So here's a thought experiment for you, Emil. So you say that we can't have a loop with an unknown number of iterations. And that's because, we're assuming that the loop is going to write some values to memory on each iteration, and so if you don't know in advance how many iterations, then you don't know the memory consumption of the function. But there's this malloc function, right?
Yeah.
So I guess in principle you could allocate, say, an amount of memory that you know would be sufficient for however many iterations the loop has, and you may allocate more memory than needed, but that would work, right?
The malloc, indeed, there are two, because in this high-level language that compiles this low-level ISA, you can indeed use malloc. But are you speaking of a malloc with compiled time known size, or a malloc where the number of the size you want to allocate is unknown or known at compile time?
Well, either way.
Because if you want to allocate some compile time known memory, you can include it in your. So it's easy because it will be included in the overall footprint of the function. So it's easy. When you write malloc with a value which is not compiled time known, what will happen is that the memory will be allocated somewhere else, not in the frame, and then you will hint this value as the location of this allocated frame. But if you want, so for instance, you are in this frame, you want to malloc x with x an unknown value. What will happen is that, for instance, the allocated frame will be here of size x, but then each time you want to modify one value here, you need to dereference because it's not in your frame. So you need, for instance, if you want to access this value, you need to dereference to store it, and then if you want to addition with this value, you need first to dereference to store it, addition, and then dereference back here. So you need to use deref a lot, and it can be expensive. And that's why I would suggest, in this case, to jump, like to define a new function, to jump in this context, do the computation you want to do, in which you don't have to use deref, and then jump back at your function.
Mm-hmm. Okay, so in essence, you could have a loop with an unknown number of iterations. If you can put an upper bound on the memory consumption, it just wouldn't be a good idea.
I think yes.
Okay, that makes
yes.
sense.
I think you could indeed, you're right, using deref, but it would be costly. But it could work.
Understood. Okay, thank you.
Actually, maybe if your footprint is like really slow, your idea may be more optimal. Yeah.
Maybe sometimes.
Yeah.
And yeah, I remember you saying that you allocate memory and sometimes part of it is unused.
Yeah.
Is it fair to say that if you were to do kind of two passes where the first pass kind of determines how much memory is actually used, and then the second pass kind of compresses everything, you should be able to remove all the zeros?
This is already done, no?
Yes, actually. There are two things. There are the because this is due to the thing that the two passes are due to the Poseidons. But I can talk. This is like a little bit another subject, but we can enter. If we are done with this, I can talk about Poseidons. But first,
I don't want to derail the conversation.
Yeah. But I will answer the question. But is there any more questions related to jump, deref, etc., etc.?
I'm good.
Okay. So. Okay.
There are already two passes, and I think that we could do more things into the first pass.
The thing is, we need a Poseidon precompile because we will not do Poseidon by hand using it will be much more way too slow. So there is an instruction, let's call it Poseidon 16. That's perform a permutation, Poseidon permutation over 16 filaments. Actually, there is also a Poseidon 24, which is useful when you want to hash long slices. Anyway. And so there is one instruction, Poseidon 16, that will read and write in memory, but by chunks. Actually, how is it currently implemented? Poseidon 16 takes in 3 arguments, let's say A, B, and C. And for instance, an example will be easier. Let's say A equal to 2, B equal to 5, and C equal to 10. B equal to 2, meaning I will read 2 times 8, 3 times 8. Here we have 8 field elements. B equals 5, 5 times 8. This is like the memo, okay? It starts as and 6 times 8. You also have 8 field elements and 10. Here, 10 times 8. 12 times 8. You have 16 field elements. And what this means is that you concatenate, this is IAB are the inputs, you concatenate them, you obtain 16 field elements, you permutate, and you write the results here.
So then, effectively, this Poseidon 16 would have an internal state size of 8 instead of not 16. So the Poseidon here would have an internal state size of 8 and not of 16. So it's like a proper hash function, and it's not just a permutation.
The inverse, it's not. You can see it as a permutation, like no hash function. It actually can be used to build a hash function, indeed using like a sponge construction with internal state 8,
Yeah.
correct? But from the point of view of the VM, it's simply a permutation. So no notion of internal state, RAID capacity.
Okay. But I mean, just because if you compress 16 elements into 8, then
But it's compressed into 16. So this is 8, 16.
the output is 16. Sorry, I understood the output to be 8. That's why. Okay. Then.
And okay. But one key thing here is that everything is aligned. So our inputs have a length at least 8 and are aligned by 8. Like you cannot hash, for instance, the memory at index 3 to 11. Not possible. Because for the proof system, it helps a lot to have everything aligned by 8. Because you will have, I didn't talk about it for now, but you guys that you have this memory which is committed, and you have some air tables to prove the precompile, so prove Poseidon. And you will have a lookup from your Poseidon table into the memory. And due to the fact that it's aligned by 8, you can, and because we are in multilinear setting, you can use random challenges to compress everything and to reduce everything, like everything will be squeezed by 8. And so these 8 field elements will be transformed into one extension field element. And you will compress everything and you will obtain like a memory 8 times smaller, but in the extension field. And you will prove the lookup in this compressed form. And it turns out that, in particular using lookup star, it's much more efficient. So the lookups about Poseidon are almost free compared to the costly part in terms of lookup is in this memory where you have a granular access to each field element. This is more costly. Yes, please.
One question I have is, presumably every time you call Poseidon 16 the permutation, it's in the context of the hash function of the sponge. So why not just have a precompile for the whole hash function?
Like only one output? But like 16 input and you mean 8 input and 8 output?
For example.
Yeah, because for instance, in some cases, for instance, it's a fab, it's a breakpoint. For instance, the XMSS chain, we only need, so when you sign XMSS, in the chains, there are V equals 64 chains, you only need 8 inputs, 8 outputs.
Right.
So we could have a Poseidon that only to be more efficient indeed. We could have a dedicated Poseidon precompiles to do only 8 and 8. But for instance, in the Fiat Shamir, for recursion, you need the full state, the 16 field elements. Is it true? Yes, I think. Because do we really need 16 field elements? The chains, and also, for instance, in the Merkle tree, in the compression, so in the XMSS, you have your intermediate one-time signature, and then you have your Merkle tree. When you want to compress, you need at least 16 inputs to compress. So the AAB are required. And then Fiat Shamir, is it like?
First, wouldn't you be using Poseidon 24 for the Fiat Shamir to absorb more transcript into one?
I think it's in Plonky 3. I think it's currently we do like this.
I think we do 24 for the Fiat Shamir.
Okay.
I think. I filled them out at some point. I don't think it matters too much. But
I believe in WIRP3 it's the implementation is 16 field elements. And that's, for instance, one reason we need these 16 outputs. So
we can switch. No, this is just a setting that we can switch to.
Yes. But to answer your question, in some cases we only need 8 inputs, 8 outputs. In some cases, 16 inputs, and if we switch to Fiat Shamir 24, maybe we can always have always have 8 outputs. Yes, possible. Yeah. I think I should write things because
I'm writing some breakthroughs down. We already have 3.
Because there was also the idea of the thing.
Vehicle optimization.
Yeah. And also the idea with the loops that sometimes if the loops are small, don't create new function but simply deref. Okay. But I think I will remember it.
And there was the bus ride breakthrough as well. The bus ride from yesterday when you were on the bus.
I will come back to it later. Okay. Okay. Anyway, so okay, and. To summarize, there is approximately the same thing with Poseidon 24. Okay? Because we need Poseidon 24 when you want to hash, for instance, in XMSS, you have your chains, 64 chains, you obtain the 64 digests, and you want to hash the whole thing to get the leaf of your Merkle tree. And it will be 2 times faster using Poseidon 24 over Poseidon 16. Anyway. The key thing is that all those memory accesses are by 8 and are aligned also by 8. And actually, currently, in the implementation of the compiler, there is this notion of vectorized memory and non-vectorized memory. Vectorized memory, it's when it's aligned by 8 and everything is a multiple of 8. And currently there's a memory. Currently, all the vectorized stuff is at the right of your memory. Vectorize. This is at the right, and so currently, what there is like 2 passes. When you want to execute the program, maybe we can do better. I don't know. But what happens is like initially, the program is executed with a huge memory, and vectorized memory is set at the half, and the goal is that the non-vectorized memory will not clash with the vectorized memory. So the non-vectorized memory will end up here, and the vectorized memory will end up here. And then we can run again the program but now the vectorized memory starts here, and so in the end, at the second execution, we get a compressed memory without these zeros that are here. I'm not very clear, but should I repeat?
Yes.
Okay, sorry. So the memory is in the current implementation. There is like the vectorized, where everything is a multiple of 8 and so on, memory, which is at the rank of memory. And there are the non-vectorized, like normal accesses in memory. And the issue is that when you start the execution of a program, you don't know where your normal memory will end up. And so you don't know where to start your vectorized memory. And so how it's done currently is that there is two executions, two passes. In the first passes, we use a huge memory to be sure that if I start the vectorized stuff in the middle, the normal stuff will not interfere, it will be smaller, it will stay below. And so the normal memory accesses will end up here, the vectorized memory accesses will end up here, and there is some security rule because we have taken a big memory. And then we re-execute everything, but instead of making the vectorized access start here, we make them start here. Because we know that the normal memory accesses will end up here, so we start vectorized just after.
So you take the first pass to remove your security room, correct?
Yes. It's almost the same. Everything is the same as in the first phase, but there is no more this security. This
so
room.
During the first pass, you analyze everything and you know what the security room is, and so you remove it.
What's the cost of this initial pass?
Actually, it's the witness generations currently is like I would say between 5 or 10% of the whole thing, and this includes the two passes. But this could be probably we can at least 10x. I think the performance of the witness generation could be reduced by at least 10.
And you can remove the security buffer within the internal function calls on the left side as well, no? So my understanding is that when you call malloc internally on the left, you kind of allocate the worst case.
Okay.
And then you can remove the safety buffer, the same idea.
Okay. When malloc is called internally, like with normal pointers, there is not this notion of worst case. So it's you're right. That's because the thing you were speaking like some time ago is there is indeed in the end some zeros. In the end, it's not perfect because the issue is with the if-else. If you have, I think Morgan we spoke about this. I think if you have something, you have a program, else you have a different program. But imagine the if condition is much more complex than the else, and when you compile it, you need to it could be both cases. You don't know in advance, so you need to allocate quite a lot of memory in case it's the if that we enter the if. But if we enter the else, there will be some empty memory, like unused memory. And this is where why when you currently in the benchmarks you run, you will see like memory usage 95%. There are 5% remaining because of this.
But you can easily prune that in the second run, right? You could prune. Let's say you call the L.
The thing is that at compile time, there is an issue with because it must be somehow known at compile time. When you have if else, I don't know. Yes, maybe yes, indeed. But it
so it's not compile time; it's kind of runtime.
Yes.
Pruning.
Yes, I think there is, yes, we could make it work, but not in particular. It needs to be, I think, we need to put it in the end of the current frame. Okay, it's complicated, but yes, maybe. For sure, we can make it work. But it's like an optimization, not trivial, but doable, yes. Yes.
So regarding that, if we follow up on the continuation passing style, those if and else are transformed into continuation of the current computation, and so it's a separate chunk of the function.
Okay.
And so if you do this pass where you verify what's being used, you can just check that those branches of if and else are in use and then delete them and prune them, actually.
I see.
So, yeah, I think it would be worth it if you look into continuation passing style compilers. I can give you some references of books because it may be uniquely suited to what you want to do.
I see. Indeed, we can eventually we can go up to 100% of memory usage. Yes, removing all the zeros possible. Yes.
These two passes are on compilation time or on to generate the witness?
The two passes are at witness generation time.
Like we have only two programs with some limited inputs, so can we not like make a mix of a lookup and maybe some calculations?
To do only one pass?
Yeah, because
yes,
mostly because we run two programs. If not
yes, like to instead of doing two passes, to do one pass and to modify the thing a bit to make it work.
Yeah, to kind of try to guess the right amount, given that the program is always the same.
I see. Good point. Good point. We could try to, for instance, depending on the number of XMSS being signed, we could probably know. Yes, good point. I think it works.
Can you repeat?
We could, knowing, like we could have a program that takes as input the public memory and will tell you exactly, without having to execute everything, this will use this amount of memory and this amount of vectoring memory. Because in practice, XMSS is like something really predictive. So we can know XMSS will take this amount, and we can, yes, I think it works.
We can train the LLM.
Well, maybe if we make the language weaker, like if the use case we care about is really deterministic and all of this uncertainty that we're discussing does not apply, then maybe we can just build sufficient conditions into the language to ensure that determinism, and that could make things easier.
Yeah, even we can also restrict the number of XMSS signatures that we aggregate to power of 2. And we know what would take for 512, and 24.
Yes. But even if it's not power of 2, we could recompute between 1 to 2,000 to 10,000 XMSS. We recompute everything and you have a table. So yes, it works. Because this is not something enshrined in the verifier. This is something that only the proven. So if it's yes, definitely it works. Okay.
There's a coffee break in 10 minutes.
Yeah, okay.
I don't know if we're doing question.
Just to kind of
got the breaks.
when you write there with slide 16, you said like A is 2 and B is 5, right? Like technically, of course, that should be like a multiple of 8, given that it should be 9, right? That's what you said. And so like 2 and 5 here would be kind of like in this space of extension field elements, right? To some extent. Like if you want to have 5 to be a valid or even 2 to be a valid kind of a line value, right? So like you said explicitly, like for example, you couldn't have the values from 3 to 11.
Yes, correct.
Yeah. So like in that point of view, like 2 and 5 are also not sensible values. They're only sensible because we are treating them as being multiples of 8.
Yes.
Yeah. So then with Poseidon 24, what do the inputs look like? Is it like
Okay.
8 and 16 or?
Yeah. Currently, with Poseidon 24, I think so. We have same ABC. This is to make the arithmetization simpler, obviously. And I will say so 2, 5, and 10. Same example. And so you take, if I recall correctly, yes, yes, 2 times 8 to 4 times 8. So here you take 16. So for A you take 16. For B, 6 times 8, you take 8. And here 10 times 8. 11 times 8, you only take 8. And what you do, you concatenate the 16 with the 8, you obtain 24 field elements, you permutate, and you keep the last 8. And the last 8, this chunk here, you write it here.
Okay.
Because it turns out we only use the last 8 field elements of the permutation.
So the Poseidon 24 actually has a smaller output than the Poseidon 16.
Correct.
Okay.
Is there a reason you don't give the Poseidon 24 just 3 inputs, like 3 inputs to size 8? Like, is there a reason you force the first 2 to be concatenated at all times?
Could we do like 8, 8, and 8?
Yeah.
Not currently, but we could imagine doing it. But this has some advantage because the advantage is that there is only 3 values, and so you're because there is if you look back at the add and null, there is always often 3 memory access per cycle, and so every instruction can access at maximum 3 memory cells. And if you want to add like a 4th parameter, A, B, C, and D, you would need a 4th memory access per cycle. And so this would likely slow down a bit. But it could be doable, but actually,
Wait, so there's some requirements previously coded where you only want to do 3 memory accesses for each, like you want each instruction to have the most 3 memory accesses?
yes, this is to make it simpler, but nothing forbids we could design a system with 4 memory accesses. But actually, the Poseidon 24 is not used very much. So, for instance, I think it's only used currently in XMSS to hash the internals publicly, and in this case, actually, we you need this 8 to take into account the state. Like you have your state and you want to incorporate new information, so your 8 will be your state, and this 16 will be the additional part that you want to ingest, and that's why using only 2 arguments it's sufficient, I believe, in the current situation.
Okay.
So if all we're using it for is to hash the winternet's pub key,
Yeah.
why not have an opcode that's just hash the winternet's pub key?
We could do it. Yes.
But for recursion, it complexifies things.
As I believe, we also use Poseidon 24 to hash the leaves of the weird Merkle trees, because like weird Merkle in weird at each step you commit to polynomial, but the leaves in practice are 64 to 128 field elements that you need to hash. and to speed up this hashing, you need Poseidon 24. So actually, you also need Poseidon 24 in recursion.
The other thing worth mentioning is that we have a stretch goal for leanVM, which is to be a VM for general purpose hash-based cryptography with all sorts of other use cases beyond Ethereum R1. Maybe at the application layer, maybe other blockchains, maybe for privacy wormholes, which is the same thing as Zcash but on Ethereum R1. And if we have this virtual machine be adopted by the whole industry, then more eyes on it, more performance, more security.
But actually, in both cases, whether it's XMSS, like the Winternews pub key, or the hashing the leaves of the weird Merkle tree, in both cases, is you have a bunch of like 100 feed elements or 1,000, and you want to hash it. So we could imagine a precompile that takes the start of like a shift offset, and you hash the whole thing. So it could be an idea.
A variadic Poseidon.
Sorry?
A variadic Poseidon.
Yes. So you hash a long chunk of data. Yes, why not? Definitely.
Yeah, maybe the answer why not is it would be hard to make a circuit for that.
I think that's like a silly question here, but what are we trying to compile down to these opcodes? We take say word, are we trying to compile like the set of verifier checks of like how the verifier checks the prover's trace? Is that what's getting compiled to this? So you take you have word that you've written. So you could try and compile like what the prover's doing in word, but that seems like that's not what we need here, right? Like,
No, to verify.
So it's just trying to compile down the set of checks that the verifier does on the prover's.
Yes.
This is what you have written in lean DSL.
Okay.
So basically, you receive the Merkle commitment, sample some random indexes, open, verify the Merkle list, fold, some check, etc.
Basically, like you have like the verifier file of where that is rewritten in the DSL.
Okay.
Break?
Yeah.
No, right.